Okay, good day, students. Welcome back to DBMS course. And now we're moving to the next sections of chapter 2, which is part 2 of the ER and EER model. So in this part of the chapters, we will study about the keys. So you will understand the key as the attribute or set of the attributes that is used to identify data in the entity sets. And then the DER diagram itself. So you will know what it looks like, the diagram, the relationship of between the entities. And then after that, you will learn some types of the entity sets. And then the next, the EER model will be discussed. So it's the enhanced entity relationship model. And the last sections of these chapters will be about the reductions of ER and ER diagram into a table. So let's just start it with the first part of these chapters. It's called keys. So we will understand some part of keys, some types of keys, and the relationship with the entity sets. Alright, as you can see in the slides, there are 6 types of keys. There are super key, and then alternate key, candidate key, secondary key, primary key, and foreign key. So we will look into each of them in the next slides. Super key. So a super key is a set of one or more column, or we can say attributes, that can uniquely identify a row in a table. So every table must have at least one super key. For examples, in a table with columns of student ID, email, phone number, all the three together, or even any two of them, can act as a super key since they can uniquely identify a student. Next, we have what is called candidate key. So candidate key is a minimal super key, meaning it's a super key with no extra columns. So it uniquely identifies a row in a table. There can be multiple candidate keys in a table. For example, if student ID alone can uniquely identify a student, so it's a candidate key. Similarly, if email alone can do the same, so it's also a candidate key. Next one, we have a primary key. So the primary key is one of the candidate keys chosen to uniquely identify rows in a table. So it is the main key, okay? And one table can only have one primary key. Or we can usually simplify by using P key, P and K. As the examples, if we have a student ID, a student table, the student ID is chosen as the primary key. Why? It because student ID will be used to uniquely identify each row in the student table. Each student will have one student ID, and there won't be one student have two student ID, right? So one student will have one student ID. which means the student ID is uniquely identify one student. And the next one we have what is called alternate key. So the alternate key is any candidate key that is not chosen as the primary key. For examples, a student table. If the student ID is the primary key, then email, email is also the candidate key, will be considered as a alternate key. Okay, so it's alternate key, so it's any candidate key that is not chosen as the primary key. As the examples, if we have student table, then the attributes of which is chosen as the candidate key can be also chosen as the alternate key. All right, we have a secondary key. So a secondary key is a non-unique key which is used for retrieving data, but it cannot uniquely identify a row. Yeah, for examples, if many students can have the same course name, yeah, we can use the course name as the secondary key to find all the students enrolled in the particular course. So the course name is the secondary key. It cannot identify or it's not a unique key used for retrieving data, but you can use to find the particular uh, value that you need to retrieve, something like that. And the next one we have what is called foreign key. So it's the last types of key. So a foreign key is an attribute, or we can say a column or set of columns in one table that refers to the primary key and another table. Okay, I repeat again. A foreign key is a column or set of columns in one table that refers to the primary key in another table. Okay, and it is used to establish a relationship between two tables. Okay, that is foreign key. So later on we will more what is called we will more familiar with the foreign key and primary key. So we are not going to have the other key, but we are more focused on the primary key and foreign key. But you need to understand the other types of key as well. So examples for the foreign key, yeah, we are still in the student table. If we have a student ID in the grades table that refers to the student ID in the students table, so the student's ID in the grades table is the foreign key. Okay, maybe you are still a little bit confused, so let's check on the next slides for your better understanding. So let's take a look at the following examples. Let's break down the keys in the following tables. Yeah. So we have table 1, which is employee ID, and then we have employee name, license, passport, and DID. DID is the department ID, okay? So but for the super key, yeah, I will start from the beginning. For the super key is any combination of columns that can uniquely identify a row. Okay, so for table 1, the sorry, I need to use the, okay, the laser to, okay. So for table 1, the following examples are the super keys. Yeah. Employee ID, and then the employee license, passport, yeah, and then the employee ID with the license, employee ID with the passport, and many more combination. So that is the super key. As you can see here, that super key consists of the primary key, candidate key, and the alternate key. So that was the super key. The next one is the candidate key. So the candidate key is a minimal super key, meaning it can be uniquely identify a row with the fewest possible attributes. Okay, for table 1, uh, the employee ID and then license, passport can uniquely identify an employee. Okay, so these attributes, this one and this one, making them a candidate key. Okay, so candidate key is the employee ID, employee license, and the employee passport. That is the candidate key. Meanwhile, for the primary key, so the primary key is the candidate key chosen to uniquely identify rows in the table 1. So the primary key here is only one column, yeah, only one column. So it's the employee ID because one employee can only have one ID, right? So in this case, the employee ID is selected as the primary key. All right, the next one is the alternate key. So the alternate key are candidate keys that are not selected as the primary key. So here we have the license, employee license, and then the employee passport. These two are the alternate keys because they are candidate keys. They are not chosen as the primary key, but we can have this to retrieve a data uniquely from a table. Yeah, so we have these two as the alternate key. Okay, the next one is called a secondary key. So the secondary key are the non-unique keys that are used for data retrieval purposes. They are not shown in the diagram explicitly, but an examples might be the ID column. Okay, and it could be used to find all the employees in a specific department, even though the ID might not be unique. So the ID is the examples of the secondary key. The next one is a foreign key. So the foreign key is a key that establishes a relationship between two tables. Okay, this foreign key. In table 1, the ID in the table 1 is a foreign key that refers to the ID in table 2. Okay, so this is the foreign key in the, sorry, this is okay, sorry. So the ID in table 2 is the primary key, but in the table 1 the ID is the foreign key. Okay, so I repeated that again. DID, department ID in table 2 is the primary key, but department ID in table 1 is the foreign key. Okay? Got it, right? All right. So let's move on to the table 2. So we have columns of department ID and destination. So it's the department, okay? So in table 2, we have a super key. Yeah, super key. This is a super key because it's a unique key, okay? In a table 2. And then the department ID is the only candidate key in the table 2 because it uniquely identifies each department. So the department ID is also considered as the candidate key. And as I said before, department ID is also work as the primary key in table 2. Okay, since table 2 is quite simple, it doesn't have alternate key and the department ID column in table 1 acts as the foreign key, like I've just said before. And the foreign key here connects these two tables and forcing a relationship between the employee's department and the department designations. Now let's move to the next section of this chapter, which is called the entity relationship diagram. So we will study more about the logical structure of the database with using this kind of diagram. All right, so this is the entity relationship symbols. You need to uh, refer to this list to make an entity relationship diagram. So I will just skip this and I will jump into an examples to make you have a better understanding. Okay, examples 1. So make an ER diagram having two entity sets. It's between the customers and the item. Okay, so I will start by drawing an entity here, the customer's entity and the items entity. Okay, so I need to draw a relationship between these two entity, right? So I will draw the relationship between these two. So the connections or the relationship between the customers and items is purchase, right? So customers purchased an item. So I will draw the symbols of relationship here. So that is the purchase. And next one, I'm going to draw the line between this entity. Okay, so customers represents the people who make the purchase, and then the items is the entity represents the product that customers buy. Meanwhile, for the purchase, this is the relationship entity, which is connects customers and the items. Is represents the act of purchasing. And next one, I will draw the line over here just to connect between the entities and the relationship. Okay, so customers purchase an item. Okay, So I need to start drawing the attribute symbols. So if you want to go back to the previous slides, we have attributes of a customer's ID. Yeah. So it's to identify uniquely each customer. So I need these attributes. Okay. So attributes, you need to remember that attributes need to be drawn like this oval shape. Meanwhile, for the entities is using a rectangular shape, and of course the items, and this is also the purchase, the diamond shape. Okay, so the customer's ID will be uniquely identify each customer, so the customer's ID will be considered as the primary key in this case. So because the customer ID is the primary key of the customer's entity or customer's table, so I give the customer's ID underscore. So this is how you tell the other people that customer ID is the primary key of the customer's table. You need to give the underline. Okay. So a part of the customer's ID, I need to give another details of the customers. So I will give another attribute which is called phone number, and then date of birth. Okay. And the name of the customers. Yeah. And the customer's name can be broken into three parts, which is the first name, middle name, and last name. Okay. I need to make another attributes, yeah, which is called age. Yeah, it's age, which is indicates the derived attribute. So I give a dotted oval shape because I will get this information or get this value from calculated from the date of birth. Okay, from the so the current date minus date of birth, I mean the year. So I will get this value of age. Okay, so if the value is dotted, it means that the attributes is uh, derived attribute. Okay, so it's derived attribute. So the oval shape is dotted like this. The next one, I will move into the items entity. So the items entity needs something like a primary code. So it's uniquely identify each item. So I will have what is called item ID. Since item ID is the primary key of the items entity or items table, so I give the underline. Yeah, this is how you identify an attribute is the primary key. So you need to give the underlined for the attribute. Okay. Apart from the item ID, I will have a cost, and then color and weight. Yeah, color of the items, the weight of the items, and of course the cost of the price of the item. So this is all for the items entity, and then moving to the next table, which is purchase table. So in this purchase table, I will have what is called bill number. Yeah, so bill number is indicates the integer of the purchase date. So it cannot be new. Yeah, it has to be a value, okay, and the value is 1 2 3, something like that, okay, and it can be a new, and the bill number is also a unique identifier for the purchase transactions. So I keep the underscore for the bill number for this entity. Apart from that, I have a purchase a date. Yeah, purchase date of the purchase table. Okay. Oh, I think I missed one of the. Oh no. Okay. Okay. Oh yeah, I missed one the line. Okay. So for the purchase, I need to have two tables. Yeah. Okay. So it's correct already. Okay. So the purchase also have this item ID, which is refers to the item table, and the customer's ID, which is refers to the customer's table. Okay, so we're going to connect these two, yeah, into each of the entities. So let's check later on. Okay, so I hope you understand these examples. Yeah, this is very straightforward. Yeah. So there are some advantages of using the ER models, yeah, because it's very straightforward. It's simple relationship. So the ER models make it easier to show how different parts of the database are related to each other. And of course, it's more straightforward compared to the other model. So based on the previous ER model diagrams, I believe that you already understand what the design of the database will be. And then it's easy to turn into tables. So the ER models can be easily converted into relational tables, which are used in the database, because in the ER diagram, which is we have just made before, the things or the entities and their characteristic, I mean the attributes in the ER model, can be easily turned into tables and columns in the database, because it's really straightforward. You can just see in the diagram, and then you can see that the entities or what table will have some attributes, and what the attributes are already there. The ER model is simple and easy to understand, even for people who don't have much training or wouldn't have known about the database. This makes it a good tool for database designers to explain the design to the others, for example, to users or to managers. The AR models also can be used as a blueprint by developers to create the actual database using database management software. And if you need to switch to a different type of database model, like a network or hierarchical model, the AR diagram can be converted easily. And DAR models use diagrams to visually show different parts of the database, like the entities and the characteristic and how they're connected. So it's a very visual representation, or we can say graphical representations. And it's also easy to modify. If changes are needed later, it's usually easier to make adjustment for the AR model compared to the other model. So there are a lot of advantages of the entity relationship models. However, there are, of course, always limitations or using something, including limitations of using an AR diagram. The first one is because the complexity in large systems. For a very large or complex databases, the AR diagrams can become very difficult to read. And managing and understanding a large AR diagram can be challenging. So it's a very complex if it's used in a large systems. It is also limited representations of operations. So the ER diagrams will focus on the data structures. I'm talking about the entities, the attributes, and the relationship. But it do not show how the operations, like the queries, the updates, or transactions should be handled in the database. It is also difficult in handling the complex data types. Yes, the ER diagrams may be struggling to effectively represent the complex data types like arrays or multimedia or the other advanced structures. Also, it's not the ideal for unstructured data. So the ER diagram are not well suited for the databases that deals with the unstructured or semi-structured data like documents or multimedia content, which don't fit neatly into the entire entity relationship format. It's also limited support for behavior representation. So the ER diagram primarily focus on data and its relationship, but do not adequately represent the behavior or the functions that might be needed in the system, such as the business rules or the logic. Difficulty in representing inheritance. While the ER models can represent the basic relationship, they have the limitations in handling more complex relationship like inheritance or specialization, which might require more advanced modeling technique. So that was the limitations of using the ER model. Let's move to the next sections of this chapter, which is called types of the entity sets. So here we will understand the two types of the entity sets, which is includes the strong entity sets and the weak entity sets. Okay, let's move on. Okay, so like I've just described previously that there are two types of entity sets as given below. There is the strong and the weak entity set. And we'll look into each of them one by one in the next slides. So here is a simple explanation of the difference between the strong entity sets and the weak entity sets. So the strong entity set, it's an independent. So a strong entity set represents entities that can exist independently in the database. So they don't rely on any other entity to exist. And talking about the primary key, each entity in a strong entity set has a primary key, which is a unique identifier that distinguishes it from the other entities in the same set. So let's consider a student entity set. Each student can be uniquely identified by their student ID, right? And the student ID is their primary key. So in this case, the student entity has a very strong entity set. Meanwhile, for the weak entity set, the weak entity set represents entities that cannot exist independently. They completely depend on a strong entity set to give them context and identification. So in this weak entity set, they don't have a primary key. The weak entity set do not have their own primary key. Instead, they are identified by combining a partial key, which is a distinguishing feature, with the primary key of the related strong entity. So consider a library book copy entity set where each copy belongs to a specific book. The library book copy doesn't have its own unique ID. Instead, it might be identified by the combination of the book ISBN from the book strong entity set and the copy number. So the key difference is about the existence. So the strong entity exists independently while the weak entities depend on the strong entity. The strong entities have a primary key while weak entities are identified using a combination of their own partial key and the primary key of a related strong entity. And the relationship between a strong and a weak entity. The strong entity provides the necessary identification and context for the weak entity. Let's move on to the enhanced entity relationship model. We can say ER model. So ER model is basically the enhanced version of ER model, which includes all the basic concepts of ER model with the capability to support additional semantic concepts of complex applications. And these additional concepts are including the specialization, generalization, and categorization. Before discussing the concept of the specialization, generalization, and categorization to another entity types, the superclass, supertype, and subclass will be described in the next slides. So, superclass entity type, what is it? Imagine a superclass as a general category that covers a broad group of things. Let's think of a vehicle as a superclass. It includes many types of vehicles like cars, trucks, and motorcycles. These types are more specific categories within the big category of vehicles. So anything that is a car, truck, or motorcycle also belongs to the vehicle category. And the relationship between the superclass and these specific categories is 1-to-1, meaning its specific type, for example, like car, is just a vehicle. Meanwhile, for the subclass entity type, which is also called by subtype, is a more specific category within a broader superclass. So in our vehicle examples, the car is a subclass. It's more specific because it represents a particular type of vehicle. And a subclass like car is a part of the superclass vehicle. Sometimes a subclass can be further divided into even more specific categories. For instance, car could be divided into sedan, SUV, and convertible, which is making car a superclass for these new subclasses. So, in short, a superclass is a broad category, and a subclass is a more specific category within that broad category. Now let's move on to the uh, additional concepts of the ER model. The first one is called spatialization. So what is it? Spatialization is like shortening things into smaller, more specific groups based on what makes them different. Imagine you have a big group of people. You could divide this group into smaller groups based on their job. For example, teachers, doctors, engineers. This is what a specialization does. It takes a big group, which is called the entity sets, and split it into smaller and more specific groups, yeah, the subgroups. And why is it useful? The spatialization will makes the data more organized by clearly defining what makes each group different. It is also easier to find information because when you ask a question, or we can say run a query in your database, the answer will be more accurate because the information is neatly categorized. So in simple terms, spatialization helps you to break down big general groups into smaller, more specific ones, and making your data more organized and easier to search through. Next one, we are talking about generalization. So generalization is like taking several specific groups and combining them into one bigger, more general group. So imagine we have a small groups like sedan, SUV, and truck. Instead of keeping them separate, we can combine them into one larger group called vehicle. And this process of combining is called generalization. And why is it useful? The generalization in EER model will simplify a design. So by merging specific groups into one general category, you make the database design simpler with fewer categories to manage. It is also better analysis, and it helps in data analysis by allowing you to look at all similar things together, which makes it easier to spot patterns and create reports. So, in simple terms, generalization is about combining specific categories into one broader category, making the database easier to manage and the data is easier to analyze. So let's check this diagram. This diagram illustrates the concepts of specialization and generalization in the entity relationship model, which are used to organize data into hierarchical structures. So let's break down each concept. The generalization is a process where we combine multiple entities that share common attributes into higher level entity sets. So, as we can see in the diagram, the entities employee and a customer here, over here, and customer both have attributes like the person ID, and name, address, age, and these common attributes are generalized into higher level entity called a person. Okay. So here the person is the superclass, and the employee and the customer are the subclasses. Okay. Now, spatialization. So the spatialization is the opposite of generalization. It is the process of defining a new lower level entity set from a higher level entity set by focusing on specific attributes or the characteristic. As we can see in the diagram, the person entity is specialized into two lower level entities, which is called employee and customer. The employee is further specialized into a full-time employee and a part-time employee. And these are then further specialized into specific roles such as a manager and staff and then full-time employee. Oh, sorry, the under the full-time employee, and then sales and it's under part-time employee. The sales and the collections is under the part-time employee. And customers is also specialized into different types like investors, okay, investors, borrower, with further specializations into types of accounts or loans they hold, like saving account or education loan holders, etc. So so we have an ISA relationship here. So the triangle labeled ISA represents the relationship where an entity like the employee or a customer is a specific type of a higher level entity, right? And this relationship is crucial in both specialization and generalization because it shows how the entities are related hierarchically. So, to sum up, the generalization is combine the entities like the employee and customer into the higher level entity as a person because they are shared common attributes. And then the specialization breaks down the person into more specific entities like an employee and a customer, and those into even more specific roles like a manager and staff and sales. Yeah, and the ISA relationship indicates that these entities are connected in a hierarchical manner, where the lower level entities inherit attributes from their higher level entities. And this hierarchy helps in organizing data more efficiently by recognizing shared characteristics at higher levels and differentiating specific roles or types at lower levels. Now, as we can see in the diagram, the attribute inheritance is a key concept that helps to simplify and organize the data structure. And here's how it works in the context of specialization and generalization. So the attributes inheritance means that lower level or specialized entities inherits the attributes of their higher level or generalized entities. This inheritance ensures that all the specific types of the entities have access to the common attributes defined at the higher level, while also allowing them to have their own specific attributes. So as we can see in the diagram, we have a person here, the generalized entity with the attributes of person ID, name, address, and age. And these attributes are common to all people, okay, regardless of whether they are employees or customers. And then move on to the employee and customers, which is the specialized entities. So employee and customers, both of them are inherit the attributes of person, which having the attributes of person ID, name, address, and age. The employee may have additional attributes like salary, while the customer might have a credit rating. So full-time employee and part-time employee in this case inherits all the attributes from the employee, which includes inherits attributes from the person, like the person ID, name, etc. And also the specific attributes like the salary. So they can also have their own specific attributes. For instance, the full-time employee might have a rank, while a part-time employee might have hours of work. And then investor and borrower, which are specializations of customer, inherits the attributes from customer and thus also from the person. Okay. Additionally, they may have their own attributes like a rate of interest for the borrower and why the attribute inherits is important because it's a reusability. So the attributes defined at the higher level can be reused across the multiple lower level entities and reducing the redundancy. Since the lower level entities inherit attributes from higher levels, it ensures that all necessary data is consistently available across all specialized entities. It is also simplifies the model by clearly showing which attributes are common across the multiple entities and which are specific to certain types. So to sum up in this diagram, every entity inherits attributes from its parent entities. For instance, the full-time employee inherits the attributes from employee, and the person inherits attributes from employee, and the person ID, name, salary might have the additional attributes like ranked. And this hierarchical inheritance structure ensures that all relevant data is properly organized and accessible across the different levels of the entity's specialization. So this is the examples of aggregation in the entity relationship model. So we have the employees entity, we have branch, okay, and then the job and a manager, right? These four are entities. And the relationship we have works on and manage. So works on, this shows that an employee works on a branch and it's assigned as a job. Okay. Meanwhile, for the manage relationship, this relationship indicates that a manager manages an employee working on a particular branch. So talking about the aggregation in the diagram, it is used here to represent a relationship between another relationship and an entity. So here is how it works. So the works on a relationship connects the employee, branch, and a job. It indicates that an employee is assigned to a particular job at a specific branch. Meanwhile, for the manage relationship, connects the manager to the works on the relationship. This indicates that the manager oversees an employee working on a particular branch on a specific job, something like that. So in this diagram, the works on is aggregated to form a higher level entity or abstract entity that combines the employee, the branch, and the job entities through their relationship. And this aggregated entity is then linked to the manager entity via the manage relationship. So the aggregation simplifies the model by treating the works on the relationship as a single unit, which can then be connected to other entities like manager. It helps to avoid creating multiple relationships directly between the manager and each individual entity. I'm talking about the employee, the brand, and job. So why aggregation is used? We're talking about the simplicity. So the aggregation makes complex relationships easier to understand by combining them into a single abstract entity. It also avoids cluttering the diagram with too many direct relationships, making the overall ER model more readable. It also effectively shows the hierarchical nature of the relationship where one relationship is dependent on another. So in this diagram, the aggregation is used to represent the relationship between the works on relationship, which is involving the employee, brand, and job, and the manager. By aggregating the works on the model simplifies the management of this relationship, showing that the managers they oversee the specific combinations of employee, brands, and job rather than managing each separately. And this helps in organizing and visualizing the complex interactions in a more structured manner. So when we use specialization and generalization in a database, we apply certain rules or constraints to manage how different categories relate to each other. So these rules help to ensure the database accurately reflect the real-world relationship. So furthermore, we will discuss the two types of constraints. It's participation constraints and disjoint constraints. So the participation constraints define how much a group or entity sets takes part in the relationship with the other groups. So the partial participation means only some members of a group are involved in a particular relationship. Imagine a group of students. Not all the students might be enrolled in a sports team. So only those who are on a sports team participate in a play's relationship with the sports team group. It shows that not everyone in the group is involved in that relationship. Meanwhile, for the total participation, it means that every member of a group is involved in at least one relationship. For example, in a company, every employee has to belong to a department. So all employees will participate in the works in relationship with the department group. So why it matters? It will indicate that the relationship is necessary for everyone in the group. So in simple terms, participation constraints will tell us whether only some or all the members of a group are part of the relationship. In terms of the disjoint constraint, the disjoint constraint dictates an entity which can belong to only one subclass at any given time. It's minimizing the ambiguity in classification within a database. So the superclass here, we can say an employee. So this represents a general category of employees in an organization. It contains the common attributes like person ID, name, salary, etc. that are applicable to all employees. But meanwhile, for the subclasses, which is full-time employee and part-time employee, these are specialized categories of employees, and each employee must belong to either the full-time employee subclass or the part-time employee subclass, but cannot belong to both simultaneously. And the disjoint constraint ensures that an entity, in this case an employee, can be a member of only one subclass. So for instance, if an employee, Martin, works as a part-time employee, he cannot be classified as a full-time employee at the same time. And the Martin can only belongs to part-time employee subclass. Suppose Martin was a part-time employee for a bank. According to the disjoint constraint, Martin would be placed under the part-time employee subclass in the diagram. So he will not appear in the full-time employee subclass. So as we can see in the diagram, uh, it's the concept of the categorization. So categorization is a way to represent situations where an entity can be a member of multiple entity sets, but is categorized into a single entity set. So let's break down the diagram step by step. So as you can see in the diagram, we have a U symbol over here. It's a U symbol. So it's the symbol of categorization. So the circle with the letter of U represents the categorization symbol. It indicates that the entity below it, in this case investor, okay, is a subset of the union in the superclass. And superclass is the person. This is the general entity that includes all the individuals in the system. So it's the parent entity in the hierarchy. The sub, subclasses, the employee and client, this represents two different roles that a person take to can take on. A person could be an employee of the organization, a client of the organization, or possibly both. So the diagram shows an investor can be either an employee or a client. This is indicated by the U categorization symbol. So the U symbols connects the employee and the client entities to the investor entities, showing that the investor is a categorization of both employee and client. So in other words, an investor is a special type of entity that must be categorized as either employee or a client or maybe both of them. But it's treated as a distinct entity type under this categorization. Suppose Alice is an employee in this case of the company and she also invests in the company's project. She would be represented in both employee and uh, entities. Sorry, she would be represented in both employee entity set and the investor entity set. So similarly, Bob. Bob is a client who is also invest. He will be in both of the client entity sets and the investor entity sets. So the U symbol ensures that the investor entity set correctly represents all investors, whether they come from the employee or the client entity set. So the key point about the categorization is it is used when you want to categorize entities that belongs to multiple different entity sets but share a common role or function. And the U symbols indicates that the categorized entity, in this case the investor, is derived from the union of the related entity sets, in this case employee and client. These types of modeling is particularly useful when different types of entity can play a similar role, but you want to treat the role as a distinct entity in your database. So now we are moving on to the next model is the ER model with aggregation. So the diagram illustrates the concepts of the aggregation. Aggregation is a way to treat a relationship set as the entity set for the purpose of simplifying complex relationship in an ER diagram. So let's take a look at the diagram. We have an employee here. The entity of employee represents the individual who work in the organizations, and then branch represents the different branches of the organization, and then job, which is represents the specific job or role and employee performs, and then we have a manager represents the person who manages the employees. And then move on to the relationship. We have a works on a relationship. It's a relationship between the entities of employee and branch. It shows that an employee works at a particular branch. And we have a relationship of manage. So it's a relationship that connects the manager to the works on the relationship. It indicates that a manager manages the work being done at a branch. Now the aggregation. So the rectangle closing over here The rectangle encloses the works on relationship along with the employee, branch, and job entities indicates the aggregation. The works on is a relationship between employee and branch, but it is being treated as a higher level entity set for the purpose of the managed relationship. So the aggregation allows us to simplify the diagram by treating the works on relationship along with its associate entities like employees, branch, and job as the single unit or entity when defining the managed relationship. So the works on relationship set, when combined with the job entity, is treated as a higher level entity set within the managed relationship. This means that instead of directly relating manager entity to each individual entity like employee, branch, and job, the manager is related to the aggregated unit, works on, and job. So the purpose of the aggregation is to reduce the complexity of the diagram by avoiding multiple relationships between manager and each of the individual entities involved in works on. Okay, suppose that we have an employee named Alice who works on a project at the New York branch of the company, and her job is a software developer. The works on relationship captures that Alice, the employee, works at the New York branch, and her job is a software developer. Instead of directly relating manager entity to Alice, the branch, and the job individually, the diagram aggregates this information into a single higher level entity set. So the manager relationship can now revert to this aggregated entity, meaning that the manager oversees the work done by the Alice at the New York branch in her role as a software developer. Let's move on to the next section, which is the last section of this chapter. It's about the reduction of an ER and ER diagram into a table. So we will see how the database, yeah, in tabular form, and we will see the ER diagram have to be reduced in tables. Okay, so in the ER model, we have what is called a strong entity set. That one is can exist independently. It means that it doesn't rely on any other entity for its existence. When reducing an ER diagram into relational tables, the each strong entity set is typically translated into a separate table into the basis. So as we can see here, we have department entity set with the attributes of department ID and department name. So here's how the department strong entity set with the attributes of department ID and department name can be reduced into a relational table. So suppose that we have department ID as a primary key for the table. It uniquely identifies each department within the organizations, right? Meanwhile, for the department name, represents the name of the department. So the primary key of department ID is chosen to ensure that each department entry in the table is unique. And the table is created from the department entity will contain columns for each of the attributes listed in the entity set. Every record in this table corresponds to an instance of the department entity. So this is how we transform into like this. Still based on the previous AR model, a complete attribute is one that is subdivided into smaller components, which is each representing a meaningful subpart of the original attribute. When transforming an AR diagram into relational tables, these composite attributes are typically broken down into their constituent parts, and each part is represented as a separate columns in the table. So in the table we provided, we have a name attribute that has been treated as a composite attribute, and it means broken down into three distinct components. Yeah, we have a first name, which is represents the first part of the employee's name, and then the middle name represents the middle part of the employee's name, if it's available, of course, and the last name, which is represents the last part of the employee's name. So the table structure, we have the ID, the 8 ID, the first name, middle name, last name, salary, and department ID. So the key points about this table is the 8 ID is uniquely identify each employee, which is serving as the primary key. Okay, so this is the primary key. Meanwhile, for the first, middle, and last name, these columns are collectively represents the name, composite attributes. And the table shows how the composite attribute is divided into three separate columns to store each component individually. And then we have salary. The salary here represents the salary of each employee. And department ID identifies the department associated with each employee. So the composite attributes breakdown is the name attribute, which is broken into first name, middle name, and last name. This allows for more detailed and flexible queries. For example, you can search for employees by their first name, their last name, or their middle name. It can also handling missing value. So in case where the middle name or last name is not provided, the corresponding fields are left blank or contain a placeholder such a dash like this. And this table structure is a direct result of the reductions of the composite attributes in the ER diagram, which is to ensure that each component of the composite attribute is individually accessible in the relational database. Now let's move on into the reduction of multi-value attributes. This table is an example of how to handle the multi-valued attributes when converting an ER diagram to a database table. So the multi-value attributes, sometimes an entity like an employee can have multiple values for a certain attributes, like mobile phone numbers, and instead of storing all these values in a single column, we will create a separate table to manage these multiple values. So we have a column of employee ID here, which represents the employee unique identifier, and then the phone number with the columns of list of the different phone numbers associated with each employee. And how it works, the multiple entries, even employee has more than one phone number. Each phone number gets a separate row in the table. For example, the employee with the A12 has two phone numbers, 23896 and 897. So there are two rows for A12 and each showing one of the phone numbers. Similarly, the employee with the employee ID of 51C, so she or she has three phone numbers, yeah, 1, 2, 3, and it's listed in three separate rows. This approach ensures that each phone number is stored in its own row, making it easier to query and to manage multiple phone numbers for each employee without needing of cluttering the database with multiple columns. So in summary, the table efficiently handles the situation where the employees have multiple phone numbers by creating a separate entry for each phone number and all linked to the corresponding of employee ID. Now we are in reductions of weak entity sets. So this CR diagram shows a relationship between two entity sets. It's a loan entity set and payment entity set. So the loan entity set is the strong entity set. Meanwhile, the payment entity set is the weak entity set that depends on the loaned entity. So in this case, if we are going to reduction of weak entity sets into tables, when reducing the ER diagram to tables, we handle the weak entity set, which is the payment entity set, with special attention. So here's how it's done. So table for the loan or the strong entity set includes a loan number, and then which is the primary key, and then the amount. Okay, so table name is loaned, so the table includes the loan number and amount, right? Meanwhile, the table for payment, which is the weak entity set, since the payment table is weak entity set, It doesn't have any primary key for its own. Instead, it borrows the primary key from the strong entity set, in this case, the loan number, and combines it with its own attributes, which is a payment number, to form a composite key. So here we have a loan number and then the payment number. The loan number is the primary key from loan, and then the payment number, the primary key for a payment table, and then payment date and payment account. So the loan number is the foreign key from loan table, right? Meanwhile, the payment number is the composite key, and the payment date and payment amount is included in the payment table. So loan table, it will store the detail of each loan with a unique loan number as its primary key. Meanwhile, for the payment table, we'll store the details of each payment made towards the loan. Since payment is a weak entity, it cannot exist without being associated with a loan. Thus, it borrows the loan number from the loan table and combines it with the payment number to uniquely identify each payment. So, again, the loan number, this is a reference to the loan for which the payment is made. Then the payment number, this is a unique identifier for each payment under a specific loan. And this payment date, this records the date on which the payment was made. And of course, the payment amount, which is records the amount of money paid. This structure ensures that every payment is directly linked to a specific loan, and no payment can exist without an associated loan. So consider the ER diagram that's shown before. So we are going to reduction of relationship set. Consider the ER diagram shown previously. Having relationship set works and having two participating entity sets, which is employee and department. The corresponding table is shown below. Okay, so this is how reductions of relationship sets. So we have works and entity sets. So when dealing with weak entity sets and strong entity sets in an ER diagram, it's essential to understand how they relate to each other and how to present this in tables without unnecessary duplication. So the strong entity set is an entity set that has a primary key that uniquely identifies each entity in the set. In examples, the loaned entity set is a strong entity with loan number as its primary key. Meanwhile, for the weak entity set, this is an entity set that cannot be uniquely identified by its own attributes alone. It depends on a strong entity set for its identifier. In the examples, the payment entity set is a weak entity because it depends on the loaned entity. The primary key for payment includes both a loan number and payment number. So talking about the redundancy in tables. Table for loaned entity is a table which contains the loan number, which is the unique identifier for each loan. Meanwhile, the table for payment entity. The table will have the following columns, such as the loan number, which is linked each payment to a specific loan, and then the payment number, which is identifies each payment within the context of the loan, and the payment date, the date of the payment, and the payment amount, the amount of the payment. So the relationship, the loan and payment, this represents the relationship between loan and payment. If we were to create a table for this relationship, it would contain loan number and payment number. So why the relationship table is redundant? The relationship table between loan and payment would have columns what is called loan number and payment number. However, these two pieces of information are already included in the payment table. Since the payment table needs to know which loan each payment belongs to, in this case loan number, and the unique payment identifier, the payment number, creating a separate table just to store this relationship doesn't add any new information. So in simple terms, the information you'd store in the relationship table is already present in the payment table. Since we don't want to store the same data in two different places, because it will be redundant, so we can discard or skip creating the relationship table. So in summary, we can conclude that loan is the strong entity with a loan number as its primary key, and then payment is the weak entity set that depends on loan. It has a composite key made up for the loan number and the payment number. The relationship table between loan and payment would normally connect loan and payment is unnecessary because the payment table already includes all the information needed to connect payments to loan. Thus, the information table is redundant and should not be created. So, in this ER diagram, we are talking about the combination of tables. We need to understand the ER diagram first. So we have a customer's entities over here. These entity represents individuals who take the loans. So it has attributes of customer's ID and name. And then we have loaned entity, and this entity represents loans given to customers, and it has attributes of loan numbers and amount. And we also have a relationship of borrower here. So this relationship links the customer and loaned entities. It has an attribute of income, which might represent the borrower's income, influencing the loan terms. So, talking about the combination of tables, let's consider the EI diagram shown figure below, having two entity sets of customer and loan. The relationship is many to many because a customer can take many loans and a single loan can be taken by more than one customer or joint loan. So the loan entity set is totally participated because every loan refers to some customers. So combine table loan and borrower. But loan cannot exist with any customers, so two tables are needed. Yeah. Okay, so we have a table of loan and we have table of customers. So the loan entity set is totally participated, meaning that every loan must be associated with at least one customer, and a loan cannot exist without a customer. So, given the nature of the relationship and entities, the table are designed as below. So, in case of the loan table, we have the attributes of loan number, amount, and then the customer ID and income. Okay. Since each loan must be associated with the customer, so the loan table contains not only the detail about the loan itself, like loan number or amount, but also the customer ID and income, which is associated with the borrower relationship. These design choices integrate the borrower relationship directly into the loaned table, eliminating the need for the separate borrower table. So we have a customer table here. We have a customer ID and name. So this table stores the details of the customers, and each customer has a unique customer ID and name. So we have two tables in terms of this figure: the customer table and the loan table. All right. Why two tables are needed? The loan table combines the loan details, yeah, and borrower's details into a single table, acknowledging that every loan is tied to a customer. And then the customer table keeps customer details separate, allowing for multiple loans for per customers and maintaining the many-to-many relationship between customers and loan. So in summary, we can conclude that loaned and borrower tables are combined into one table to capture the relationship effectively, which is a loan table. And customer information is kept and separate table to maintain the many-to-many relationship structure. So this design choices a simplifies data management while ensuring all the relationships are accurately captured. So reduction of generalization. So consider this AR diagram, which is shown in figure 1, in which employee is the higher level entity set and full-time employee and part-time employee in the two lower level entity sets. So we can make three tables as given below. Is the employee with the employee ID, department ID, first name, middle name, last name, and salary. And then a full-time employee table with employee ID and qualifications. And the third table is part-time employee with the employee ID, attributes, and hours worked. Okay. So, talking about the entities, yeah, I explained one by one. Okay, so the employee, the high level or general entity set. It includes the general attributes that apply to all employees, such as the employee ID, and then a name composed by first, middle, and last. And then we have phone number, and then the salary and department ID. Okay. And then the full-time employee, it's the lower level entity set that specialize the employee entity set. So it can includes the specific attributes like qualification, besides the employee ID, of course, yeah. And then for part-time employee, another lower level entity set that specialize the employee entity sets. It includes the specific attributes like hours worked, apart from the employee ID. So the generalization here is the ISA, which is a relationship signifies that both a full-time employee and part-time employee are special types of the employee. And the generalization is a concept where a higher level entity sets like employee is divided into two lower level entity sets. In this case, we have full-time employee and a part-time employee. So in this scenario, generalization is reduced to multiple tables in the database schema. So like just we have here, we have an employee table. We have full name, full-time employee table and the part-time employee table. So why only three tables? So by splitting the general employee data from the specific details of full-time and part-time employees, we ensure that the database is normalized and the data redundancy is minimized. This structure also allows the system to easily handle different types of employees without needing to store unnecessary data in cases where certain attributes do not apply. For example, store the hours worked for a full-time employee. Of course, it's not needed, okay? So the last one, we are talking about the reductions of aggregation. So these diagrams illustrates a concept in database design called aggregation. So the aggregation is a technique used to represent a relationship between the whole and its part. In this case, the whole is the job entity and the parts are the employee and branch entities. The diagram shows that the job can be composed of multiple employee and branches. This relationship is represented by a diamond shapes of works on entity, which is associated entity that connects the job to employee and branch entities. Meanwhile, the managed entity represents the relationship between the manager and a job. A manager can manage multiple jobs, so this relationship is also represented by a diamond-shaped entity, which is indicating associative nature. And this diagram also shows that the branch entity is treated as the higher entity set. This means that the branch can exist independently of a job, even if there are no jobs associated with it. So the reductions of aggregation involves breaking down a complex aggregation into smaller, simpler relationships. So in this case, we will potentially reduce the aggregation by removing the works on entity and directly connecting the job to the employee and branch entities. However, this would make the model less expressive and might not accurately represent the real-world relationship between these entities. Therefore, the aggregation in this diagram is approximately and necessary for representing the complex relationship between job, employees, and branches. Okay, that's the end of the chapter 2. If you have any question, you can just send me email at my Gmail. Okay, I'll see you in the next chapter. Goodbye.